All right, so far we've what? We've talked a little bit about probability. Um, why in a general education statistics class will they spend time talking about probability? Well, they'll spend time talking about probability because like a basic understanding of probability, which actually I've kind of assumed you kind of came into the class with. Um, Things like rules of complement and so on and so forth, probabilities between 0 and 1. We care about studying probability because probability gives us enough understanding that we can start talking about and understanding this notion about random variables. Why do we care about random variables? We care about random variables because understanding random variables helps us in terms of understanding the normal distribution in the normal random variable. So why then do we care about the normal random variable, right? That is, we kind of lay this groundwork, which is building and building and building. It's building towards something. I'm claiming that what it's building towards is the study of the normal random variable. And you spent this time doing these practice problems and perfecting these skills with normal probability, but probably a lot of the problems that you've worked on so far feel a little bit disconnected from a true underlying applied reality. So why? Why are we putting in the work? Well, here's your answer right here. And it's one of the most beautiful, breathtaking theorems that you're likely ever to see in your whole lifetime. Wow. It really does, doesn't it? I'm sorry for the silence there, but it literally took my breath away. It's the central limit theorem, often lovingly abbreviated CLT. And this is it right here. It says, consider a random sample of some arbitrary number n observations selected from a population. Any population, wowza, with a mean of some arbitrary mean mu, some arbitrary standard deviation sigma. Then when n is sufficiently large, when that sample size is sufficiently large, and we'll talk about what that means, I believe, the next slide, then the sampling distribution of x bar remembers the sample mean, will be approximately normal with a mean, right? The mean of x bar is the original mean of x, and the standard deviation of x bar is the original standard deviation divided by the square root of n. The larger the sample size, the better that normal approximation is going to be. Oh my goodness. Feel my heart starting to beat a little bit and kind of sweating, get a little bit of heart palpitations. Like, whew, this thing's a real beauty. Now, what's going on here? Let's break it down a little bit because its beauty, its miraculousness may not be entirely evident at first blush. So first off, we're saying what? We made a little bit of a claim in passing a couple of PowerPoints ago. And that claim that we made in passing is that a statistic, right, a value based off a sample, such as the sample mean, is a random variable. We made that claim, right? And that should be like a little bit intuitive because what are random variables? Random variables are random phenomenons that take different values with different probabilities, right? And the sample mean certainly fits that bill, doesn't it? That is, imagine we're taking a sample of students from Westchester University, and we're going to look at the average height of that sample. Well, whoever the tallest student is at Westchester University, I don't know who he or her is, but right, there's a certain probability that when we take our sample, there's a certain probability that that tallest student will be included in our sample. There's also a certain probability, probably a much larger probability, that that student will not be included in our sample. And depending on whether that student is or isn't in our sample, we're going to get a different sample mean, right? So what are we saying? We're saying that sample mean takes different values with different probabilities. That means that the sample mean is a random variable. On some levels, it's straightforward, but on some levels, it's very subtle and difficult to grasp. But if you're willing to buy into that, well, what have we already said? We've said that random variables have what? They have probability distributions. We've said that random variables have means. We've said that random variables have standard deviations. So the central limit theorem is really just a theorem addressing these three things. So if x bar is a random variable, the central limit theorem is just describing the attributes of this random variable. And so there's sort of three things at play: the probability distribution, the mean, and the standard deviation. It turns out the mean of x bar is always the mean of x. I know it's weird to talk about things like the mean of the mean and the standard deviation of the mean, but we're just talking about means and standard deviations of a random variable. Now, the mean of x bar is always the mean of x. The standard deviation of x bar is always the standard deviation of x divided by the square root of n. And then the statement about the probability distribution is the part that depends upon the sample size. But if we have a large enough sample, then that probability distribution is close enough to a normal distribution that we're warranted treating it as if it does follow a normal distribution, and more so using all the skills that we've previously developed to solve any type of probability question. Pretty cool, right? And this is true no matter what, right? That's the big deal, that any population part of the central limit theorem. Up until now, we've been saying assume this and assume this and assume this and assume this, and it feels a little bit artificial because in real life we probably can't make those assumptions. But the central limit theorem, in a lot of ways, is a virtually assumptionless theorem. It's a mathematical fact. It's not easily proven, but it can be proven mathematically. It could be empirically verified, and has been empirically verified time and time again, right? We call it the central limit theorem, but it's really more like a law of nature. It's really more like gravity. It says that if you do this thing right here, then something's always going to happen. You throw something up, it always comes down. You take a sample and you calculate a sample mean. As long as that sample's large enough, right, it's a guaranteed fact that it's going to follow this distribution, just like it's a guaranteed fact if you throw a ball up, it's going to fall down. And that's kind of cool, right? It's a little bit profound. It's a little bit spiritual. Now, I don't know, you may or may not be like me, where just like the very moment that you met statistics, it made you kind of think like, wow, like maybe there really is a God out there. But if that hasn't been the case, then certainly it's the case now, right? Because the central limit theorem, this law of nature, it really does make us think that maybe there's something out there that's a little bit, I don't know, like a little bit more than us, right? I mean, if it's not statistics, we all have these moments, don't we? Like maybe what? Like maybe the birth of a beautiful baby, right? Like a baby's born, and you stop and you reflect and you say like, wow, like this is life creating life. Like maybe there really is a God out there, or some higher power. Like maybe there is this sort of purpose. Like maybe there is this sort of underlying structure. Like maybe like a beautiful sunrise, right? The sun is rising and it's shining over the world and all of its entirety, and you realize that there's this cosmos out there, and that's where that sun is sitting, and you think like, wow, maybe there really is something out there, some higher power, something that maybe put together this sort of perfect world, and everything is just like, I don't know, it's just the way that it's meant to be. And so that's kind of what the central limit theorem is, isn't it? Now, before we talk more about the miraculousness of the central limit theorem, oh, hey, fun fact. What's central limit theorem backwards? Anyone know? What's CLT backwards? You're right. It's TLC. Pretty good backwards spelling. And what does TLC stand for? TLC stands for what? It stands for tender, loving care. And when something's very precious, when something's very valuable, what do? Of course, we treat it with tender, loving care, don't we? Yeah, we do. That's no coincidence for what it's worth. It's another kind of miraculous happenstance. Now, I say that a lot of the miraculousness stems from the fact that that sample mean follows a normal distribution, quote, as long as the sample's large enough. Well, what do we mean by that? What is sufficiently large? Well, it's sort of two different situations. The first situation is if the underlying distribution x that we're sort of sampling from, if that underlying distribution is normal, then it turns out the sample mean will be normal for any sample size, even a sample size of 2. It's kind of cool. Now, more realistically, more commonly, we either have something that's not a normal distribution, or we just don't know what that distribution is one way or another. It may be normal, may not be normal, we just don't know. In situations like this, a common rule of thumb is that the sample size needs to be 30 or more for the distribution of the sample mean to be close enough to normal. Now, that's not a particularly large sample, right? It's saying that all we need to do is take a sample of 30 or more, and our sample mean is close enough to normal that, right, standard convention says that we can go ahead and treat it as if it actually is normal. And so what? Well, so what? Well, using the central limit theorem, we can use the central limit theorem to answer probability questions about sample means, and we'll see the ability to do that is such a gift to statisticians. It's such a miracle. It's like a compound miracle. It's like the birth of a beautiful baby. That's the central limit theorem right there, all swaddled up for us. It's a sunrise, right, rising above the world in all its majesty. It's actually more than that. It's actually more than the birth of a baby. It's actually more than a sunrise. It's like a baby being born in the middle of a sunrise. That's what the central limit theorem is, and all of its miraculous sort of spiritual inducing sort of splendor. Let's try to get a sense of it by maybe working through a problem or two. So let's start with this problem right here. Let's say that we happen to know systolic blood pressure for patients with hypertension. Let's say we know that it has a mean of 140, and a standard deviation of 5. Let's say that X is the systolic blood pressure of a randomly selected patient. Then what is the probability that that patient's blood pressure is going to be between 135 and 145? So take a second, go ahead and solve it. I'll wait for you. So hold on, let me do it in my head. I got my X's, I'll convert it to Z's. So it's the same. So probability that X is between 135 and 145, it's the same as probability Z is between -1 and 1. So I just applied the empirical rule. That's going to be 68%. Let me raise my hand. Professor, 68%. The professor says, ha, you're wrong. What? What the? Cut the? How could I be wrong? Did you say 68%? If you did, that was a good guess, but it's a wrong guess. Wrong guess. Why? How? How could that be wrong? What is the true answer to the question? The true answer, crazily enough, is IDK. Whatever that means, I don't know. The true answer is I don't know. Why is that? I know it feels a little nitpicky. I know it feels like a trick question, but it's important. If you go back to that previous slide, you will see that nowhere in that slide did I mention that blood pressure follows a normal distribution. And the answer that we gave is predicated on it being a normal distribution. If we go way, way back to the slide about the empirical rule said for bell-shaped distributions, for mound-shaped distributions, 68% within one standard deviation of the mean. But I never claimed in that slide that it was a mound-shaped distribution, right? That question is more like a real-life question, and the sad reality of that real-life question is that we cannot answer it. The answer is, I don't know, unless we're willing to tack onto that, to layer onto that, right, a set of assumptions that may or may not be true or justified. That question is not answerable without making some assumption. If we want to assume it follows a normal distribution, then yeah, we're right, it's 68%. But if we don't know what that is, then the real honest answer is we don't know that probability. I know, it's a little sad. But don't worry, you're about to become quite happy. Now, what if instead we were asked what the probability is that the sample mean of a sample of 100 patients is between 139 and 149? So this is a slightly different question, right? Instead of asking about the probability of a single patient, we're asking about the probability of the average of 100 patients. And again, we're not making any assumptions. Technically, the underlying assumption is that we sort of took a simple random sample, that we sampled in a way that most people would consider the appropriate way to sample. As long as we took a good sample, there's no other assumptions sort of tacked onto this problem. And it turns out that unlike the other one, we can actually answer this question. So let's take a look. Well, what do we know? We know that the sample mean follows a normal distribution. Since the sample size is 100, 100 is more than 30. Thanks, central limit theorem. We know that the mean of x bar is the original mean of x is 140. We know that the standard deviation of x bar is the standard deviation of x divided by the square root of n, so 5 over the square root of 100, so that's 0.5. So we know x bar follows at least a very, very close to normal distribution, enough so that we could use all the tricks that we've spent the last couple of PowerPoints working on. We know that the mean of x bar is 140. We know that the standard deviation of x bar is 0.5. That's all we need to solve a probability question regarding a normal distribution. So the probability that x bar, the sample mean, is between 139 and 141 is equivalent to asking what's the probability that z is between 2 and minus 2. So it's equivalent to asking what's the probability we're within 2 standard deviations of the mean. And empirical rule actually tells us 95%. We're justified using the empirical rule because, right, that x bar and hence the z follows a normal distribution. Which is cool, right? It's cool because why? It's cool in a few ways. It's cool because we didn't really have any assumptions. That is, right, just because some law of God that we eventually discovered, it turns out that sample means are always easily solvable. The probabilities of sample means always could be solved using this sort of specific distribution. Wow. It's kind of crazy. It's also cool because this finally gives us a way, doesn't it? It finally gives us a way to actually answer a question that's perhaps been plaguing us for quite some time. At the very, very first PowerPoint, I talked about statistics and parameters. I talked about samples and populations. I said that researchers are often interested in the population mean, but the population is too vast to look at. And because of that, we don't know the population mean. So we settle. We settle for taking a sample. We look at the sample mean. And I said the sample mean becomes our best guess for the unknown population mean. Now, a natural question is, how good of a best guess is it? And the central limit theorem allows us to very explicitly answer that question. If you were to ask me why is the sample mean a good guess for the population mean? I would say to you, because it's very likely to be very close to the true mean. Now, you might ask me, what do you mean by very likely? What do you mean by very close? And the central limit theorem allows us to answer both of those questions, right? In this particular example, we could say that, right, we're 95% likely, the sample mean is 95% likely, there's a 95% chance that the sample mean will be within 1 unit, 1 millimeter of mercury of the true mean. So again, we can see that the sample mean is very likely to be very close to the true mean. How likely, how close? Well, there's a 95% chance it'll be within 1 millimeter of mercury of the true mean. That's how close. Right? The central limit theorem allows us to very precisely measure how good of a best guess the sample mean is. And as we will see, this creates the engine, this creates the motor that drives all of the statistics moving forward from here. That is, if there was no central limit theorem, there would be no confidence intervals because the central limit theorem is what powers confidence intervals. If there was no central limit theorem, we wouldn't have hypothesis testing because the central limit theorem is what powers hypothesis testing. If there was no central limit theorem, we probably would not have the field of statistics, or it would be much smaller and far more marginalized than it is right now. Central limit theorem is sort of what powers our profession. If we think back to like an earlier discussion of means and medians, we said at a glance the median appears to be the superior way of measuring the average. It's more intuitive, right? It's the 50th percentile, whereas the mean is this kind of weird like center of gravity thing. The median is resistant, right? The median is not unduly influenced by a few outliers where the mean is. So, right, based on those things, the median seems superior, and it seemed a little perplexing that nonetheless we lived in sort of a mean-dominated world. We lived in a world in which people, right, use the mean so much more than the median that when we use the word average, to most people that's synonymous with mean. Why? Why do we live in that mean-dominated world? Well, the answer is the central limit theorem. The central limit theorem is so powerful and so profound that we want to use it whenever we can, which means that we want to use the mean whenever we can. So again, just to summarize what I just said, we always say that the sample mean is a good best guess for the typically unknown, well, I should say population mean. Why? Because it's very likely to be very close to the true mean. How likely, how close? We saw that the central limit theorem allows us to answer both of those questions very explicitly. I don't know about you, but I really feel like taking a moment and giving thanks. It's actually what I gave every Thanksgiving when we go around the table. This is the first thing that I always give thanks to. Yeah, much to the annoyance of my wife. Now stop. Do practice problems too. So go through them, do practice problems, reinforce all the skills in terms of central limit theorem. I believe should be answers to all the odd problems just like before towards the end of the PDF. When you feel like you've perfected these problems, then you're ready to move on to the next PowerPoint. Happy holidays.